First I'll start by showing you some of the results we got from the electron microscope analysis. Now these are different sieve sizes. This is your key, your mineral key here, which of course you can't see, I'm pretty sure. But what this tells you is, among other things, it allows them to do a statistical analysis of what percentage of which minerals are at those different, in this sieve fraction, how much percent is what. But it also tells you, as you'll notice, the pink, which I believe is dolomite here, and the blue is quartz, and the brown is the iron oxide, and the iron oxide is where the gold is. And so the iron oxide at plus 50 mesh is still pretty well broken away from everything else. That might be attached to that, but probably not. So we only need to get down to like bigger than 50 mesh to get good liberation of the iron oxide, because the gold is in the iron oxide. The gold is extremely small and it's going to be very difficult to get by itself. Now, these are actual images of the particles. I'm not sure exactly what the scale is, but you see kind of shadows here? Those would be the other minerals in the particles that it detected the gold. You can see there's many here where the gold particle is so small it doesn't even print. When you go down here, this is basically the same thing but with the other minerals dark enough to do some good. And as you can see, all the way down to here, there's some dolomite, and all the way to here before you get anything else besides dolomite and iron oxide. So that's basically where the gold is. Primarily it seems to be in the iron oxide. So we're looking at concentrating the iron oxide. Here it gives you some of the percentages of the various minerals in this particular ore, or actually this particular sample of this particular ore. This lets us know, which wasn't surprising, that the quartz and the dolomite are tougher than the iron oxide in general. The iron oxide tends to crush fine a little easier, which may be useful. Here's actually some pictures. This is iron oxide. There's a little gold particle there. And dolomite over here. Quartz, lead sulfide. Again, it's amazing the resolution that this gives. And to give you an idea, this is a single gold particle, and that's about 20 microns, and yet you can see pretty good surface detail in it. And here's various other gold particles. Now, because of the preliminary tests, we wanted to see, first of all, if a magnetic separation would work, if a low throughput but high precision gravity separation will work, and we may do some flotation experiments here in the near future. The magnetic separation was complicated by the fact that the screened fraction that we used of the original sample was it had dried, so it kind of clumped together and didn't break up real well for the test. So I will be doing a wet magnetic separation myself later. We'll show you that anyhow. And then the wet gravity separation on the Moseley table, it looked like it did a pretty good job of getting us a gravity concentrate. We've got the heads, tails, cons, to be sent off for assay here shortly, and then we'll actually have some results. So let me get to the actual stuff so you can see what they did. So here we are back at camp with Montana B ore, and we're going to try some magnetic separation. I've already taken a head grade. Rick here is getting things cleaned up and ready. Looks like a vibratory feeder to me there. Got to make sure everything's clean so you don't get cross-contamination.
Do
you know how these work?
For different metals?
Okay. What happens is you have a slurry of particles. As it runs down, the denser particles cut the corner and wind up segregating to the inside of the spiral, the lighter particles to the outside, and then you adjust this gate here to make a split. When it works, it's extremely efficient.
And this one is for coal. Apparently they need different pitches for different materials, I would guess.
Yeah. So the magnet makes things stick to the belt while it goes around the roller.
I might slow this down just because I'm getting some carryover here.
Sure.
There we go. Yeah, that's better. You can see it's hanging on too long and getting carried out over this end stop.
Okay.
There's some dust here.
Yeah.
Now it's mostly just catching there or dropping before it.
Yeah.
Slower's better, right off.
Small particles. And it's still bringing a lot of clumps there. There must be some pretty magnetic material in there, huh? Now this is a Mosley table. As you can see, this is not a high production unit here. Laboratory scale.
Oh, you know what's wrong? I'm sorry. Totally screwed this up.
So this is Montana B that was run through Jimmy's impact mill there that we were testing yesterday. And this is the V-shaped tabletop, which handles a little coarser material.
Full water bottles.
And it will also have a little bumping action in this direction as it works. So we'll see how this works. Supposedly stay right there, they will not move. It's got a little bit of a shallow
right, depending on how much we tilt the table.
Okay. So there we've got the, I'm guessing that's mostly magnetite there.
Okay.
Because I mean it's so dark.
Dark, yeah.
You know, there's no red to it at all.
You probably got all three in this one.
Yeah. So I think that's a good place to stop there.
Okay.